Welcome back. So if there's one topic that's probably more at the core of more areas of applied math than any other, it has to be matrices. And how do you damage matrices and still let them reveal what they have inside of them? So we have a great sequence of talks by Petros and Michael going to go through random Nézet matrices.
Great, thank you, Mike. And thanks for the invitation, and it's a great opportunity to actually be here. For the next 3 hours, we're going to be talking about the application of randomized algorithms to numerical linear algebra. And this is a two-part tutorial, just like everything else. And I'll do the first part when I'm going to talk mostly about the past, what has been done over the past 15 years in terms of applying randomization in numerical linear algebra and matrix computations. A little bit about the present, some more recent results. Then Michael is going to pick up after the lunch break, and he's going to talk a lot more about the present and also some future directions, including showing how you can do matrix computations on terascale matrices, something that is pretty hard actually using traditional tools. Numerical linear algebra is an area where randomization is not a resource. It's not desirable, people didn't like it, and perhaps it appears a little bit when you want to do something like the power method and you start with a random vector, or you want to compute a Krylov subspace and again you start with a random vector. But really that was the extent to which randomization was used in matrix computations and numerical linear algebra. With the advent of big data, of course, the situation has to change. To a certain extent, you are not going to be able now to deal with the matrices that appear in applications today, which could be terascale or even larger. And at that point, you're going to want to do something a little bit more efficient than that. Now, in theoretical computer science, randomization and sampling are well-known resources that you basically use in order to design provably accurate algorithms for problems that are massive or computationally expensive. So if you have matrices that are so large that they are not going to fit in random access memory, then what you want to be doing is perhaps sample, work with a much smaller matrix. If the matrix fits in RAM, then there are many tools that are going to handle them very well for you. LAPACK, has been doing that for decades, I guess, and it works very well. But if you are looking at secondary memory, slow memory, then you want to perhaps think about randomization and sampling. The other case where randomization and sampling are very useful is to design approximation algorithms for problems that are computationally expensive or perhaps even NP-hard. And you don't associate numerical linear algebra with such problems. Numerical linear algebra, you are thinking matrix multiplication, eigenvector, eigenvalue computations, regression, solving systems of linear equations, and so on. And those are all polynomial time operations. But once you start thinking about matrices as data, then you can have things like feature selection. Select a subset of columns from your matrix, where now the columns, say, represent features. And there, you are getting combinatorial optimization problems, such as the column subset selection problem, which has actually been studied for a while in the numerical linear algebra community, which is expensive. And there, even for medium-sized inputs, like the ones that I'll actually show examples in a bit, the problem becomes intractable fast. Again, you can throw randomization and sampling to speed things up. This is going to be one of the prototypical examples that we're going to see actually throughout the tutorial, both my part and Michael's part. One of the successes in randomized numerical linear algebra has been the idea of sampling rows and columns from a matrix. Matrices, at the end of the day, are about rows and columns, so you can sample a few rows, you can sample a few columns, create a smaller matrix, and work on that smaller matrix. And the question is, how well can you approximate various quantities from the original matrix using this small matrix? This is the example that we're going to be working through, at least the first part of my tutorial, matrix multiplication. A fundamental operation, you have two matrices A and B, you approximate their product by picking a few columns from A, the corresponding rows from B. So you create these smaller matrices C and R, and you approximate AB by CR. You want to argue that some norm of the difference AB minus CR is small. And you sample, so there's going to be failure probability there. You don't want to sample uniformly at random. Think of A, for example, having one non-zero column. Then basically, uniform sampling is not going to pick that particular column with any reasonable probability. So you want to do something smarter than that. And we're going to be showing exactly what you want to do. An alternative way to get around this need for, let's say, adaptive sampling, elaborate sampling, weighted sampling, some non-uniform sampling, an alternative way to get around this is to pre-process your input matrices. And the ideas there are going to be to hit the input matrices with sort of random projection type matrices, which spread out the information in the matrices. So now, even if you had a single non-zero column in A, if you hit it with a random projection matrix, that information is going to be spread out. Now you can do uniform sampling. So these two ideas, we're going to argue that they can be treated more or less within the same framework, basically. So you either do some careful sampling, or you pre-process, and then you can do uniform sampling. And we'll see exactly what we can get. Once you have some idea of how your sketch behaves, so this is your sketch, these columns, these rows, then you can use matrix perturbation theory to basically argue that the smaller matrices, your sketch, is similar in terms of, let's say, spectral behavior to the original matrix. And structural results that basically decouple this randomized part, this first part here, which has failure probabilities and everything, with the deterministic part, the matrix perturbation theory part, are very useful to better understand how some of the algorithms behave in practice. And we're going to be discussing some of this as well. There is a clear interplay between theoretical computer science. The idea of randomized approximation algorithms is coming from theoretical computer science, with, of course, numerical linear algebra, where matrix computation, matrix perturbation theory has been central for many decades. These things are not just theoretical. They've been applied in real data. I'll show a couple of examples. Actually, one example. Michael is going to show more in his part of the tutorial. But certainly, matrix computations are fundamental in data mining, information retrieval, machine learning. So anything that you are doing to speed up the fundamentals can be applied into big data and can be black boxed there. So this is the roadmap of the tutorial. The focus will be on sampling rows and columns, sketching matrices by sampling rows and columns, or via random projections. The fundamental machinery, the thing you have to understand in order to be able to work in this area, is approximating matrix multiplication. So we're going to spend a fair amount of time discussing this. Decoupling randomization from matrix perturbation, I'm going to show at least one result that does that, so that you can basically plug in better methods to sketch matrices there and directly get better results. So this is going to be in red, my part. We're going to start with a little bit of motivation, and the motivation will be to speed up matrix computations. Also interpretability in terms of data analysis. I'm going to discuss both issues. Approximating matrix multiplication is going to be the second part. From matrix multiplication, how do we get to computationally more efficient singular value decomposition and other matrix factorizations? A bit of improvements and recent progress at the end of my side of the tutorial. Then Michael is going to talk about least squares problems, another very important problem in numerical linear algebra, statistical perspectives on least squares problems. This is going to come back to what Mike Jordan was talking about yesterday when he was talking about perhaps biased estimators. I'm going to be talking about unbiased estimators, but you can introduce bias, and perhaps it gives some advantage. Theory and practice, how to move on to things like the Nystrom method, kernel approximations, and so on and so forth. And finally, the implementations on large-scale settings. Can you do matrix computations on the terascale, basically? Areas that we are not going to cover in this tutorial that deserve perhaps a tutorial on their own, and we'll hear about them actually in various workshops. Matrices are not just about rows and columns, they are also about elements. So an alternative would be, let's sample elements from the matrix. Dimitris Achliokos and Frank McSherry did that in 2001, and they had some bounds back then, relatively weak, but it was a new idea at that point. Then more recently, people like Emmanuel Candes, Ben Recht, Terry Tao, Martin Wainwright, and others have worked on basically getting exact reconstruction. So being able to do the matrix completion, as it has been called, getting exact reconstruction for matrices that have certain fairly restrictive assumptions. And removing those assumptions is ongoing work. The other area that we're not going to say anything about is the holy grail of numerical linear algebra, which is solving systems of linear equations. There has been a long line of work, about 10 years old now, starting with very fundamental work by Dan Spillman and Senghua Teng, who basically argued that you can solve systems of linear equations with Laplacian matrices as input, so very specific input matrices. They correspond to graphs. in time that is proportional to the number of non-zero entries of the matrix without dependence on condition numbers. And if you think about any other method, conjugate gradients and so on and so forth, this is a spectacular progress basically, but for a very specific class of matrices. Moving beyond Laplacians looks pretty hard. If I have time at the end of my part of the tutorial, I have a couple of extra slides for each one of those methods that I will try to show. There are surprising, I put a question mark because I don't know if they are surprising, connections between all three areas. Raw column sampling, element-wise sampling, solving systems of linear equations. There are very nice connections there. For example, here matrix multiplication is one of the toolboxes, one of the tools that has been used to get better results, with a couple of other additions, of course. So, let me start with a little bit of motivation. Why do we want to do randomized algorithms in numerical linear algebra? And let me show a couple of pictures. So for the past several years now, actually, I've been working on the analysis of population genetics data. And one of the things, the first thing you learn there is that, of course, the human genome across different individuals is highly similar. And an often quoted number is 99%, but actually the real number is probably a little bit lower. Of particular interest are locations, loci in the genome, where we are different, because these loci in the genome account for phenotypic differences, taller, darker skin, and so on and so forth, but also predisposition to diseases. Cancer, diabetes, heart diseases, and so on and so forth. SNPs is one particular type, single nucleotide polymorphisms is one particular type of variation across the genome that has been very well studied. They have received a lot of publicity. There are lots of those locations in the human genome. There are about 10 million or so. The specific structural property, if you care about the biology just a little bit, is that out of the 4 possible alleles, A, C, T, and G, exactly 2 appear in locations that are SNPs. And you can see here some of those locations. The columns here correspond to SNPs, and for example, in this column, it's 2 alleles, A and C. So G and T do not appear there ever. The kind of data I get from my collaborators when we do population genetics analysis have the form of a matrix. The rows correspond to individuals, and you get a few thousand rows. The columns correspond to SNPs, and these days I get 2 million, 2.5 million columns. And they have genotypes. The entries are genotypes, but because of the specific structure that you have, the fact that the SNPs have 2 out of 4 possible alleles, it's very easy to encode them numerically, not of interest for this particular tutorial, but just keep in mind that at the end of the day, you're going to deal with a matrix like this one. Thousands of rows, millions of columns, and potentially you are combining many different data sources. So this can very easily get large. It's not, I don't know what we want to call big data. This is not necessarily going to be tera scale, but they're going to get pretty large pretty soon. The reason that, by the way, this has... I'm sorry?
In this example, there are just entries themselves are very limited, right? It can be 1 in 6.
Correct. So the entries themselves, in this particular case, every column has 3 possibilities, basically. So this is a matrix at the end of the day of 0, 1, and 2. There are many ways to encode, and it doesn't really matter for our purposes. The reason, by the way, if you've read about SNPs in the news for some reason, this is the reason they have become so popular is because they are used in the so-called genome-wide association studies. So you have those individuals, let's say half of them, 1,000, have a disease, the other 1,000 don't have the disease, and then you look every single column and you check, is there some correlation between that particular SNP and the disease? You run chi-square or something, right? And then you go back, the SNPs lie within a certain gene, and you try to formulate some hypothesis about the pathway of that particular disease. Genome-wide association studies and SNPs correlated with diseases, I mean, they make it in the New York Times all the time. We're going to use it a little bit different here because I actually want to motivate principal components analysis. We're going to use it to reveal population structure. So I'm going to combine data, and I use this example because these are publicly available data that I can easily share if you are interested. The Human Genome Diversity Panel is an effort that started actually with Luca Cavalli-Sforza at Stanford a while ago. They collected about 1,000 samples, 52 populations throughout the world. So you can see there is Africa, Europe, Middle East, Central South Asia, East Asia, and Native American populations. Let's join this with another very well-known effort, the HapMap Phase 3 data, another 1,200 samples, another 11 populations. Let me highlight one population, the Mexican population. It's an admixed population with genetic influences both from Europeans and from Native Americans. And the resulting matrix here, after all is said and done, pre-processing, merging carefully, and so on and so forth, you get about 2,200 rows, 2,200 individuals, genotyped on about 450,000 SNPs. So it's about 1 billion entries. It's a dense matrix, not anything massive, but certainly something that you're not going to be able to immediately handle. Let's run PCA, so mean, center, and project on the top 2 left singular vectors, and you get a picture like this. So this is the projection of 2,200, roughly speaking, samples on the top 2 left singular vectors. Remember, the left singular vectors in this case are going to be what has been coined in the population genetics community as an eigensNP. They are basically left singular vectors, linear combinations of all the SNPs. We project there, and we get a picture like this where population individuals from nearby populations cluster together. So you have Africa, Middle East, Europe, Central South Asia. The Mexicans are out of place. We'll see why. The colors signify different geographic regions. So this is blue for Africa, this blue circle for Middle East, Europe is green, so I know that the legend is pretty small, but they signify different geographic regions. Okay? This is nice. You are getting sort of a map, if you want, from just genetics data. It also coincides quite a bit with the out of Africa hypothesis. So Population Genetics 101, our species, Homo sapiens, started somewhere in Africa, then moved towards Middle East, spread to Europe, spread to Central South Asia, East Asia, crossed to the Americas, probably through the Berings, but there have been other hypotheses, to populate the Americas about 20,000 years before present. And again, you can see that this is a pretty similar line, what you get. This is called a C-line, a Klein. Is it satisfactory? I mean, these pictures make it in the science section of New York Times, so people like them, but what exactly are they signifying? They are projecting data on eigensNPs, left singular vectors, linear combinations of everything. What you would really like, you have no intuition about linear combinations of loci in your genome. What you really like is basically actual SNPs. So is it possible to get actual SNPs that span the same subspace as these eigensNPs? Actual SNPs you know a lot about. People do a whole PhD thesis on a particular gene. SNPs lie within genes, so you might have a lot of intuition about actual SNPs and actual genes, but very little about linear combinations of things. So one question here would be, for interpretability, instead of having left singular vectors, eigensNPs, let's get actual SNPs. Yeah? So, I mean, I don't want to get too much into this interpretation. This is just a picture. This is not proving anything about the out of Africa hypothesis and so on and so forth. This is just one piece of evidence showing this line, this continuous line. There are many other techniques that you need to use. One thing that I didn't mention is that this is a projection on 3 principal components. You can see that the Mexicans lie in between now the Americans and the Europeans, which is exactly where you would expect them to be. Issues. So getting back to sort of the numerical linear algebra issues, first of all, one question would be computational efficiency. You got a matrix with 1 billion entries, 2,200 by, say, 450,000. How efficient is it to compute principal components analysis on this matrix? In my laptop, it takes 12 minutes, so no big deal. It's not one-liner in our version of MATLAB because you cannot load this whole matrix in RAM. You have to load it in pieces, but it's doable. However, in a recent paper this year in Nature Communications, we had to run an SVD on a matrix that analyzed 14,000 samples. Now you have a 14,000 by 14,000 matrix. Now an SVD there becomes much trickier. And anybody who's done real data analysis, this group included me, population geneticists, medical doctors, biologists. You never run one SVD. I mean, everybody has an opinion. Let's remove those samples and rerun it and see what happens. Let's do whatever. Let's move a whole population. So you run hundreds of those at the end of the day. And this is not the only analysis you do. You have other analysis to do. So you want something efficient that basically can give you some approximation to the top several singular vectors fairly fast. How much do you care about accuracy? Do you need machine precision? Do you need 10 decimal digits? No. The data are noise. I mean, in this particular paper, we're actually looking to characterize the connection between the ancient Minoans, ancient DNA basically that we extracted from ancient bones, to modern Europeans, Northern Africa, Middle Eastern populations. And if you go to my webpage, you're going to see a lot of press releases that picked up this particular story because there has been a lot of archaeological evidence and a lot of interest in the community about what were the ancient Minoans. But the point is that getting machine precision, 10 decimal digits on data that are probably already noisy, have missing entries and whatnot, doesn't help much. You just need a ballpark figure. And that you can get from approximation algorithms, basically, and randomized methods. So the problem, yes, because this one, and again, I'm hiding some details, the way you do it is by computing AA transpose. You end up with a 2200 by 2200 matrix, and the SVD there, eigendecomposition, is fairly easy. This one is not easy, okay? So one issue is computational complexity, and the issue is just going to get worse, of course. The other issue is that you want interpretability, so you want to select good columns from your matrix, basically the way I described before, and that's a hard combinatorial optimization problem, the column subset selection problem. Interestingly enough, the two problems are related. If you can approximate the singular vectors, they give you indications about which columns are good to select. If you can get good columns from a matrix, then those columns contain approximations to the singular vectors. And hopefully that information will be conveyed later in the tutorial. So let's get a little bit more technical here. We are looking at a matrix A. This is what the SVD does. It approximates A as left singular vectors, this M by K matrix of left singular vectors. Let's take the top K times some X. It's a very good thing. We know exactly what this X is, by the way. No concerns here. It's the top K singular values times the top K right singular vectors, or just UK transpose A. There are many ways to write the low rank approximation. It's optimal with respect to unitarily invariant norms. So this is the best rank A approximation you can get with respect to unitarily invariant norms. But the columns of U sub K, they are linear combinations of potentially all your columns in your dataset. So they are hard to understand, hard to interpret, hard to tell what they signify from a practitioner's perspective. And one of the things we had proposed with Michael a few years ago was to replace these left singular vectors by actual columns from the matrix. So instead of left singular vectors times X, get actual columns times X. What do you want here? You want A minus CX is not going to be as good as the best rank A approximation, so you want it to be close to the best rank A approximation. How many columns do you want? Well, if you are looking for the rank K approximation, you'd like to get as close to K as possible. And the good thing is that now you have interpretability. You've lost a little bit of accuracy, we'll see how much, but on the positive side, you got interpretability because you have actual columns from your data, and that's what practitioners understand well. What is easy, what is hard? Computing X is easy. With respect to any unitarily invariant norm, it boils down to least squares. So that's not a problem. Finding out which columns to include in C, that's combinatorial optimization. So that is the difficult part there. That is the column subset selection problem, and variants of it are actually NP hard, and it has been studied in the numerical linear algebra, but getting better and better solutions is something that has happened over the recent years. Here's the kind of theorem you'd like to get. You'd like to get a theorem saying that A minus CX, and by the way, the best X you can get, if you are familiar with least squares, you can see it almost immediately. It's just the pseudo-inverse of C. This is a generalization of the inverse for matrices that are basically rank deficient, times A. So basically, the best solution you're going to get is the projection of A on the subspace spanned by the columns of C. You want this to be 1 plus epsilon close to A minus AK. And this thing here is the best rank K approximation to A. The projection of A on the subspace spanned by the top K left singular vectors. Okay, so we project A on the subspace spanned by the columns we selected, and we compare that to the projection of A on the subspace spanned by the top K left singular vectors. We'd like to be 1 plus epsilon close, and I have a number of words here. We'd like an efficient algorithm, small number of columns, how big is going to be C, reasonable probability. Let me quantify them a little bit. Later we're going to see theorems. We'd like low degree polynomial in Mn and K. So if A is an M by N matrix, we'd like a low degree polynomial on M and K. There is a lower bound on K over epsilon. You are not going to get better than K over epsilon in terms of the columns that you include in C, so you'd like to be close to K over epsilon. Reasonable probability, just pick your favorite. You can do constant and repeat a few times, or you can actually prove that certain algorithms have higher probability and others have almost exponentially high probability and so on. Yes?
In your example of the studies, how small would you have?
So that's the good thing. That's
the Frobenius norm.
so. Perhaps I should remind people actually what the Frobenius norm is. It's the sum of the square root of the sum of the squares of the entries in the matrix. So this is a bit of an element-wise, on average, what happens in terms of the deviation. So there is going to be definitely a disconnect between theory and practice. So depends on what kind of epsilon you are after. If you are after 10 to the minus 10, all these things are inapplicable, basically. You're going to have to do something very different. In practice, however, we're going to see that you are able to select something very close to k plus 10, and still get very accurate approximations. Why? Because real data don't behave like worst case instances. This is a general example, this is a general theorem, holds for any matrix A. You're not going to be able to break it. Real data doesn't necessarily behave like that, and this theorem tells you nothing about much nicer special cases.
Matrices have good rank K approximations of Frobenius.
So they do, some of them do actually. In the genetics case, it doesn't. It doesn't have a good rank K approximation, but this still doesn't matter. I mean, the error that you're getting here, the rank K approximation simply means I believe that the top K singular vectors and singular values are the important thing. That's what I want to analyze.
So somehow this is like a proxy.
Correct. This is a proxy for the low rank approximation. Works regardless of whether this is small or not. Okay? Simply, yeah.
At is that maybe there's a different objective function.
Oh, absolutely. Absolutely.
Operator norm.
Sorry?
Operator norm.
We'll get to that. Okay. Good questions. We'll get to some of those in the open problem session, but let me just clarify the reason we're proving things for the Frobenius norm, the spectral norm actually we're going to prove a couple of things about, is because they're simple to prove. They're unitarily invariant and we know how to handle them. Moving to other norms that could be of much more interest to practitioners, we don't know. And I'll set that up as open problems. Yes?
Even absent analytical results, do you have any intuition on what properties of matrices, whether they're statistical properties of real data or whatever, kind of put real-world data, matrices that come from data, in the kind of happier category than the extreme cases that are sort of pushing the edges of the results in the theorem, to give us any sort of insight, even if it's just from experience?
A great point, and I'm not going to speculate live. I'm happy to do it offline. Yeah, that's a great point. That's exactly what we'd like to get at, right? I mean, this is sort of the point of the semester. I mean, it's one thing to prove something for arbitrary matrices. It's a very different thing to say, here's a family of matrices that sort of behave like the SNP matrices. What is it that we can do? All our empirical results are way better than anything that the theory predicts. Okay? And by the way, SNP matrices behave very different from document term data and so on and so forth. So eventually you're going to need some different model for the different areas. If you want to understand row and column sampling, the fundamental building block, which now goes back 15 years essentially to papers by Ravi, Santos, and Alan Fries, and the other papers that I've also been involved in, is matrix multiplication. So let's discuss this. It brings back happy memories, I guess, from Joel's talk yesterday, and we'll see how. Matrix multiplication. M by N matrix A, N by P matrix B. You are looking to approximate the product AB, and I don't want you to think of matrix multiplication as the ijth entry of the product is the inner product of the ith row of A, the jth column of B. Instead, that's the way you've probably been trained to think of matrix multiplication. Instead, I want you to think of matrix multiplication as a sum of n rank 1 matrices. So, A times B is exactly equal to the sum of the ith column of A times the ith row of B. That's an outer product, so you get n by p matrices. You sum up all those n rank 1 matrices, and you are getting exactly the product A times B. Once you look at matrix multiplication like this, approximating it through randomized algorithms becomes fairly obvious. Simply, instead of looking at all those n sums, terms, just pick C of those. So let's do that. So fix a set of probabilities that I'm not revealing yet, the PIs, and pick C out of those n terms with respect to those probabilities, and do it in IID trials with replacement so that the analysis is simple. You're going to have to rescale when you sample in order to make your estimator actually unbiased, but later Michael is going to bias the estimator. And you end up with this approximation here. So this is your original sum. This is the approximation. You now pick C terms only. Each term that you pick, you rescale it by 1 over C times the probability. And now you've made it unbiased. I'm going to introduce two different notations because they're going to be useful down the road. The exact same procedure, which intuitively I described as subsampling basically a sum of n rank 1 matrices, the exact same procedure can be described in terms of actual matrices without thinking of that subsampling, as you have A and B, you pick a column of A, the corresponding row of B, you include the column in C, the row in R. So you form these two smaller matrices C and R, and you now approximate A times B by the product CR. Again, we're going to do non-uniform sampling. We're going to pick with those probabilities PI that I'll discuss in a minute. And we're going to rescale prior to including in C and R in order to get a nice formula for the expectation. These are the probabilities. We're going to pick a column of A and the corresponding row of B with probability that is proportional to the Euclidean norm of the column times the Euclidean norm of the corresponding row. So what are we doing? We are biasing ourselves towards rows and columns that have larger elements. Why? Because they affect matrix multiplication more. Larger entries basically affect the product more. And notice here that the particular rescaling, if you include a column of A in C, you rescale by the square root of C times the probability, because you rescale also the corresponding row, this should be a C, you rescale the corresponding row of B by the square root of C times the probability. When you multiply them out, you get exactly the same formula that I had before. One more notation, one more piece of notation which actually will be important. You can think of this matrix C, which consists of a few columns of A, as a product of A times a sampling matrix S. Now a sampling matrix is basically going to be an n by C matrix, so it takes you from A to a subset of columns of A. So it's going to be this n by C matrix. It has one non-zero entry per column, indicating which column you picked, and the corresponding value in that column is basically just the rescaling factor. So I introduce this matrix S, and now I can write the product AB, which is approximated by C times R. C is exactly A times S, and R is exactly S transpose times B. And S is sparse, has one non-zero entry per column, C non-zero entries overall. This is just notation so far. The main idea is that instead of looking at those n rank 1 terms, you just keep C of those, and there are three different ways of writing this down. It's easy to implement. You can do this sampling in two passes. In the first pass, you compute the probabilities. In the second pass, you actually keep the columns and rows. We don't know how to do it in one, and it doesn't look easy. Element-wise, the expectation of CR is equal to AB. So you get an unbiased estimator, and that's regardless of the sampling probabilities. If you want to minimize the variance, basically the Frobenius norm error in this case, then you pick the particular sampling probabilities that we chose. So those were not arbitrarily picked, they were picked to minimize the Frobenius norm error. It's a nice exercise for a graduate class to actually prove this theorem here, that in expectation, the Frobenius norm of AB minus CR is less than or equal to 1 over the square root of C, this is your sample size, times the Frobenius norm of A times the Frobenius norm of B. There is nothing deep here. This is direct manipulation of the expectation. Okay, you just use properties of the expectation and the variance. Straightforward. This one is a little bit more involved. You need a martingale argument to prove matrix concentration. So notice that this is just expectation. If you want to prove high probability, you can run a martingale argument and it works. And since we have a bound for the Frobenius norm, we immediately have a bound for the spectral norm as well. So the spectral norm is upper bounded by the Frobenius, the operator norm, whatever you want to call it, the L2 norm. So that is basically the largest singular value of the matrix, or basically how much the matrix deforms the unit ball. It's directly bounded by the Frobenius norm, but we'll do better. Let's look at a special case where B is A transpose. So now instead of B, you have A transpose. You are looking to approximate AA transpose. By CC transpose, there is no R now. Basically, you pick a few columns. The same columns become rows. And the bound becomes 1 over root C times the Frobenius norm of A squared. Just vanilla, plug it into the previous formula. I want to talk a little bit about the sampling probabilities. Basically, to approximate AA transpose, what I'm saying here is that pick columns of A with probability proportional to the square of their Euclidean norm. Okay, so columns with larger entries, pick them with high probability. The nice thing is that for this particular case, you can get a better spectral norm bound. And this is exactly where you use the machinery that Joel was talking about yesterday. I'm going to have two assumptions here. The first one is going to be that the spectral norm of A is going to be 1. Not important, just normalization makes my life a little bit easier. You can easily remove that. The Frobenius norm is at least 0.2. Again, not important, but it simplifies this formula here, and there are other ways to get around this. So both of these are not that important. What is important is that you need to set the number of columns that you pick to be at least that much. And if you go below that, the result breaks. Then for that particular setting, you get a bound for AA transpose minus CC transpose, the spectral norm, the operator norm now, that is at most epsilon. So you get a considerably stronger bound that we had before. Comes from matrix Bernstein, I'll say a couple of words later. These don't matter, you could just get a spectral norm here as well and get rid of the first one. This assumption here is just to make my life simpler here. I could have a more complicated formula here and you would get the same result. The third one, though, is important. The constants have been worked out, and depending on which particular matrix Bernstein inequality you apply, you're going to get slightly different and perhaps a little bit better constants. The proof is simple. This particular proof is using the result by Oliveira that Joel mentioned yesterday. Very nice, very clean application of the result. Takes less than a page to prove. Similar results were actually known since 2006 or 7 by Mark Rudison and Roman Versingin, except they were using the Khinchin inequalities that, again, Joel was talking about yesterday. Much heavier machinery, a lot harder to understand and use. This result, vanilla application of the matrix Bernstein inequality by Oliveira. Important thing, and we've made that mistake, that's why I'm highlighting this again and again, C has to be sufficiently large. The Frobenius norm bound holds for any value of C. The spectral norm bound holds for C being sufficiently large. Below that, you don't get a result. Open problems. As I was preparing the tutorial, I realized that we know things about the Frobenius norm, the spectral norm. We don't have non-trivial upper bounds for other unitarily invariant norms. And of course, the obvious choice would be the other Sutton P norms, and in particular, the trace norm. Would be nice to get something non-trivial. We don't have anything. Other non-unitarily invariant norms. Is this algorithm useful for non-unitarily invariant norms, the L1 norm, the L infinity norm, entry-wise things? We don't know. As far as I can tell, I haven't seen much there. So far what I did is I approximated the product A times B by CR, where I basically picked a few columns of A. This was the sampling matrix that was sparse, and I included them in C and the corresponding rows to include in R, the corresponding rows of B to include in R. What if I replace this sparse matrix by dense matrix? So the sparse matrix has the advantage that it's a sampling matrix, so you subsample a few columns, a few rows, but why don't we try something dense? And let's try one of the popular choices yesterday, which is the random sign matrix, Rademacher random variables. So this is plus minus 1, forget about the rescaling, doesn't matter, it's there to make the expectation work out, plus minus 1 with probability half. What do you get? Well, you get pretty much the same results. I'm going to show actually the spectral norm result first, because this is the most important, the most interesting one. This is coming from work by Magen and Zouzias last year in Soda, and what they proved is that you get a bound for AB minus CR, the spectral norm, that is epsilon times the spectral norm of A times the spectral norm of B, again, as long as you sample sufficient number of columns and corresponding rows. What is sufficient number here? You have to sample at least the stable rank of A, the stable rank of B. If you don't remember what the stable rank is the ratio of the Frobenius norm square over the spectral norm square. The stable rank is indicating how spread out the spectrum of the matrix is. So a stable rank of 1 means that the matrix is basically rank 1. A stable rank of n means that all the singular values are basically equal to each other. So it's very spread out. So you need to sample at least the stable rank. Let's bring it in our parlance basically by making the same assumptions that I made a couple of slides ago. So B is going to be A transpose, and B is going to be normal, and A is going to be normalized now. So the spectral norm is going to be 1. Let's see how different it is to pick a dense matrix S as opposed to a sparse matrix S. So the same setting, but now I'm looking at AA transpose as opposed to AB, and the spectral norm of A is 1. You get exactly the same bound that I had before. So you get AA transpose minus CC transpose less than or equal to epsilon. you get a number of samples that depends on the Frobenius norm of A square over epsilon square. That's exactly what I had before, but the logarithmic, the term inside the log changes a bit. Before I had the Frobenius norm of A square over epsilon square, now I have just the log of n. And for different choices actually of dense matrices, this is one particular choice for a dense matrix. For different choices, this term here is going to change. This will remain the same. Why do we, yes?
Maybe this is probably a really silly question. I'm just missing something, but a number of these results require estimates on a couple of the norms to pick the constants. Like C, you need to have estimates or actually know the values of spectrals and Frobenius norms and others. And so I'm wondering, is there, for practical usage, computing those norms in and of itself can be a very expensive operation if the matrices are really, really large.
It's one pass over the matrix, so they depend. This particular result depends only on the Frobenius norm. The specular norm is expensive. The Frobenius norm is one pass.
Yeah, the specular norm is easy. But for those that need spectral norms, do you use estimates or?
So at this point, the way I'm stating this is as theory.
Okay.
As we're going to see, the way I'm going to apply this, you'll actually have an idea about what those norms are going to be. They're going to be applied to fairly special matrices within other machinery later on. But in general, we don't use estimates. Of course, you can use estimates, and you will have a little bit of deviation there in terms of the bound. But right now, the Frobenius norm square is basically one pass over the matrix, and most of the results I'm showing just depend on that for now.
Can I ask a question?
Yeah.
Can you go back one slide? Because that appeared, you present it as a necessary condition on C, but you could instead state it as that the upper bound is just the Frobenius over root C times some root of log. That would be
It's
quite
not
equivalent.
exactly like that, actually. So I'm not going to go through the proof, but actually this breaks down if you make it very small. This is going to break down if you make it very small. You're not going to be able to apply the Bernstein inequality, basically, at some point. Okay?
But I mean, you could have put the stable rank here. I mean, yeah,
Here, on the right-hand side.
Yeah.
Yeah. So that I can put. Yeah.
that maybe was not.
Yeah. That I can do. Yeah. Why is it good to use a dense matrix? Because the second result does not need careful sampling. Before, I needed to sample with probability proportional to the Euclidean norm of a column times the Euclidean norm of the row. Now, I had nothing like that. This particular dense matrix, it's not sampling anymore, it does something else, it creates linear combinations of columns and rows, is oblivious to the input matrix. It's reminiscent of random projections, of course, of the Johnson-Linde-Strauss lemma, the plus minus, the random sign matrix has been used to reduce dimensionality while preserving norms. The Frobenius norm bounds, by the way, are the same as they were for the case where S is just a sampling matrix. Again, we need a sufficiently large value to apply this theorem properly. Holds for arbitrary A and B. Again, it should be a simple exercise to modify the previous sampling bound to generalize to the case where you have two different input matrices, A and B, but we haven't done it, so I didn't put it up there. But again, this should be a nice exercise, I guess, for Michael's class. What is nice here is that there is no reason to constrain ourselves to just a sign matrix. And actually, multiplying AES and S transpose B, computing that product for the random sign matrix, is relatively expensive. It takes just the regular matrix multiplication time, whereas you could use much better matrices, dense matrices, such as the subsampled Hadamard transform matrix, the work introduced by basically Nir Ayalon and Bernard Chazelle, and Thomas Sarlos in Fox in 2006 did that, and then we did that with Thomas, Michael, and Mutu in 2011 in another paper. And the advantage here, of course, is that now you can compute the matrix-matrix product faster, because this is a Fourier transform type algorithm, so it is faster. And recent progress, the best paper actually award in Stock this year, a few months ago, was given to a paper by Ken Clarkson and David Woodruff, who introduced an ultra-sparse random projection for which we have a very similar result to the matrix multiplication result, and actually this appears in a paper in Stock as well by Michael and Jean-Louis Meng. So this technology basically, let me recap it, I think I have it here. So if I recap this, what we're saying here is that you can approximate the product AB by AS S transpose B, where S is, for example, a sampling matrix. The advantage being that you are picking actual columns of A, actual rows of B. You get those two different bounds here. And you can also get a dense matrix S here, something like the random sign matrix. You don't keep actual columns, actual rows, so you lose that part, but you form linear combinations of columns of A and rows of B, and you're getting the same bounds basically, modulo some difference in the load factor. Okay. So this is matrix multiplication. This is going to be a fundamental building block that I'm going to use in the next few minutes to argue about how to go to fast SVD, how to go to CXCUR approximation. So are there any questions so far? Yeah.
So, well, this is more of an application question. Have you tried or have you discovered or applied your approach to discover different types of genetic variations other than SNPs?
So we've only done SNPs. I know other groups have used this approach for STRPs and other type of polymorphisms. But SNPs, I mean, the reason we've done it mostly on SNPs is because there are millions of those. STRPs, there are way fewer. So what other kind of genetic variation do you have?
Also in a different context, not the human genome. So I would think this might be very useful in metagenome analysis where you have many organisms.
Yeah. We haven't done it, no. But again, I see what you're saying, but we haven't done it. Yeah.
Another kind of applied question, possibly, again, silly. If your columns were to be, instead of SNP type data, if your columns were to be time series, so you had basically data where every column was a time series, do the results, like the column selection problem, do they hold under Fourier transformation of the data invariantly, or is there a change? I just can't kind of work out the algebra in my head of what happens if I Fourier transform the columns and take them into the frequency domain. What happens to these results?
So I'd say no, a priori at least. But again, I think Michael's going to show something on time series. Yeah, but it rotates things a lot also. It mixes things up. So I don't know, off the top of my head.
I just can't see
if it's a full rotation, of course everything remains the same. But again, it depends a little bit on what exactly you have there. Yes.
So we have a new QR algorithm for doing column selection that's under certain conditions optimal, and it only touches the data once. So it'll be interesting as the semester goes along to compare the behavior of these different kinds of algorithms.
So it is QR and selects columns, or it builds a matrix Q?
Yeah, it selects columns.
Okay, sure.
So for the procedure on the SNP data, whether this is invariant coding of the SNPs, for example.
It is. So there are 3 different encodings, and it doesn't matter. As long as you mean center your data, they're all identical.
I mean, if I give you 016 to code...
Oh, no. Okay, so you need to do something reasonable. So you can do, you have to do symmetric around some numbers. So 016 won't be symmetric. So 012 minus 1, 0 plus 1, any reasonable encoding would work. This would be an unreasonable encoding, so it wouldn't work, yes.
But SNP is essentially a type of categorical data. Why? I mean, what's the meaning of just calculate a linear combination of these things?
I very much agree, except that people do that all the time, so that's exactly what we're trying to do. Instead of having linear combinations of SNPs, we're trying to pick actual SNPs, not have linear combinations. But for example, as I showed, the projection on the top left singular vectors, the linear combinations, gives these nice plots, and people like them because they're just nice plots to a certain extent. They're not necessarily directly interpreted. Yes?
Do you have any intuition of using the dense S like this? Because if you use sparse S, you can regard it as a variable selection.
That's exactly what it is, yes. Yeah. So the dense S, we're going to use it to get approximations to the singular vectors. And hopefully I'll get to that in a little bit. They will both be used. The sparse S is basically feature selection, variable selection. The dense S will be used for computational speedups. We'll get to that. Okay. So let me get back to what I said about the CX factorization. These are columns. This is an X that you can compute given the columns. This is the theorem you want. You want something like A minus Cx less than or equal to 1 plus epsilon times the best possible, but with actual columns. I want to connect these type of theorems to matrix multiplication. And the first thing I'm going to do is I'm going to derive a very simple connection to matrix multiplication. It will take less than a page to do. It's going to be actually not for the Frobenius norm, it's going to be for the spectral norm, just because it's a bit simpler to put everything in one slide. In the interest of time, I'll skip that and go directly to that derivation here. So this is A minus Cx spectral norm squared. Factor out A, and you are getting I minus Cc plus. This is a projection matrix. It's a projection on the subspace perpendicular to the subspace spanned by the columns of C. Okay? Expand this. The spectral norm square is basically the spectral norm of this matrix times the transpose of the matrix. So you get something like that. I minus Cc plus, AA transpose, I minus Cc plus transpose. Just the spectral norm here, no square anymore. And now we're going to subtract Cc transpose from AA transpose. And you can do that without changing this norm at all, because the projection of Cc transpose on the subspace perpendicular to Cc transpose is, of course, 0. So this property right here. And now you are left with this formula here, but these are projector matrices. They do not increase unitarily invariant norms, so you can drop them with a less than or equal to. And we connected A minus Cx to matrix multiplication. This is a deterministic result, always holds. So if you improve matrix multiplication, you've improved this particular bound. And now we can apply the technology we have for matrix multiplication to say something about A minus Cx. And for example, one of the things you can say, and this was in the early papers with Ravi, Santos, and Alan, and Michael, and all these people, is that if you are picking columns of A with probability proportional to the Euclidean norm square, you're going to get a bound like this one, for example. 1 over, it's the fourth root once you do the algebraic manipulations, the fourth root of C, the column size, the sample size, times the Frobenius norm of A. Okay, and takes a couple of pages to prove, modulo, of course, knowing something about this bound here, which I gave in the previous slides. Is this good, is this bad? Well, obvious caveats. You are doing sampling with replacement, so even when C is equal to n, you are not going to get a 0 error. That's fine. That's perhaps not, that's not the most important problem. What is important is that if A had rank exactly K, so if A was a low rank matrix, you would like A minus Cc plus A to be really small by just picking K columns, because you can pick K linearly independent columns, and then the projection of A on the subspace spanned by those columns is going to be exactly the original matrix A, so this error here is going to be 0. And we know how to do that. Numerical linear algebra, we very well know how to do these things. However, this is not what you get here. Even more, you'd like for matrices whose numerical rank is small, let's say, so the information that you care about is concentrated on the top K singular vectors, you'd like to get an error that scales with A minus A sub Kf, not with the Frobenius norm of A, but the Frobenius norm of A minus the best rank K approximation. That's the scale that you'd like to have here. And that was the column subset selection problem, and the results for that existed in the numerical linear algebra community going back to work by Gene Golub in the 1960s. Of course, we do have such a theorem now, and this is not the strongest theorem we have, but it's a theorem, so I'm going to show this one. There exists a way to pick columns from A. How many? K over epsilon square log K over epsilon square, so that A minus Cc plus A is 1 plus epsilon close to the best rank K approximation with constant probability in this case, and you can improve on that if you want. What's the algorithm? Same as before. You set up a probability distribution over the columns of A. Those PIs, PJ, so those probabilities Pj summing up to 1. I'm not revealing them just yet. We'll come back to that in a slide or two. You pick K over epsilon square log K over epsilon square columns with respect to those probabilities in C IID trials. And you let C be the matrix consisting of those columns. That's the algorithm. And the claim is that once you pick the algorithms with those carefully constructed probabilities, you're going to get A minus Cx to be 1 plus epsilon close to the best rank K approximation, basically. To the error of the best rank K approximation. Yes.
So for your algorithm, the complexity is ln squared.
Correct.
That depends on k.
Correct. For this particular algorithm, the complexity, we'll see why it does not depend on k, because basically I'm doing something a lot more brute force than I should. So potentially you could do something better. This is going to come in the next slide. So give me just a minute, but that's a great observation. One of the things to say here is that C has actual columns from A, no rescaling at all. The reason this happens is that I'm projecting A on the subspace spanned by the columns of C. Rescaling doesn't matter. You can rescale those columns. The actual subspace doesn't change at all. So I will include rescaling in the proof because it's necessary there, but I can drop it from the final theorem because this doesn't affect the subspace spanned by those columns. Again, just a technical point. What is important, of course, is to reveal what are the sampling probabilities. What are the probabilities that make this theorem go through? This is the best rank A approximation to A. Left singular vectors, singular values, right singular vectors. The rows of this matrix are pairwise orthogonal and normal. The columns we don't know much about. So the columns of this matrix, the only thing that you know is that they have a Euclidean norm that is between 0 and 1. It's the Euclidean norm of those columns that you want to use as your sampling probabilities. And we'll actually see why when we go through the proof. So the PJs, the probabilities with which I'm going to sample columns from A, are going to be the Euclidean norms squared of the columns of VK transpose. Normalized, of course, to sum up to 1. Why do I have the order mn squared time? Because in order to compute VK transpose, I'm just going to run brute force SVD. In principle, all I need is the top k right singular vector. So if I have a better way that depends on k, then the running time would be order of whatever time I need to compute VK transpose. But certainly I know how to do it in order mn squared. So that's the reason I'm just dominating the running time by that. These probabilities have a name. They are called leverage scores. And I believe Mike Jordan was the one to point it out to us. They've been used in the statistics community for outlier detection. If you want to figure out which columns of A are influential for your singular value decomposition, these are the columns you should bias yourself towards, the columns that have high leverage, because those affect the SVD more. Let's see how the proof goes. As I promised in the beginning, one of the fundamental building blocks for proofs in this area are basically structural results that sort of decouple the randomness from the matrix perturbation theory part. This is one such result. Here's what this is saying. It's saying that A minus Cx is less than or equal to A minus AKF, that's the best possible error, plus the Frobenius norm of this term here. What is the Frobenius norm? What is this term here? A minus AK. Again, that's the residual from the best rank A approximation times some matrix S. This is going to be actually either our sampling matrix or a dense matrix, exactly the stuff we talked about in matrix multiplication, times the pseudo-inverse of VK transpose S. This particular bound holds for any n by C matrix S. It doesn't have to be just the sampling matrix or just the random projection matrix, although those are the ones we're going to use, as long as the K by C matrix VK transpose S has full rank. So this is deterministic, this is a structural result. It holds always as long as this matrix here has full rank. This is a K by C matrix, and the only thing you need here is that it has rank K. C is larger than K, so you need this to have rank K. Proving this result actually is not that bad. We're not going to do it. This result holds if you replace this norm here by any unitarily invariant norm. So you don't, this is pretty general. I'm only showing it for the Frobenius norm, but we have applied it for the specular norm as well, and we haven't applied it, for example, for the trace norm, but we are doing something now. The proof critically depends on the fact that A minus CC plus A, our particular choice for X, is the best possible choice for unitarily invariant norms. So basically, setting X to be C plus times A is the arg mean over all matrices X. It's the best choice. However, analyzing this best choice is hard. So what you do is you analyze suboptimal choices for X. And that's the most critical observation in the proof. I'm not going to go through that, but instead of analyzing this quantity here, you analyze a different quantity, slightly worse, but much easier to analyze. Okay? And gives this particular inequality at the end. Variants of the results have appeared in various papers, including the review that Joel and Perganer, Martinson, and Halko had a couple of years ago. Let's see now how we're going to use this result to get a result for A minus Cx being close to A minus AKF. First of all, we need Vk transpose S to have full rank. Otherwise, we cannot apply this particular structural result. For that, I'm going to go back to matrix multiplication. Look at this. This is Vk transpose Vk, and that's identity. Vk is an orthogonal matrix. This is my approximation to Vk transpose Vk, using the sampling matrix notation, let's say. I pick sampling probabilities that depend on the Euclidean norms of the columns of Vk transpose. These are the leverage scores. That's how we came up with the leverage scores here. We pick the sampling probabilities that make this matrix multiplication approximation result work. This is less than or equal to epsilon as long as you sample enough, and we sample enough. That's what we do. And we pick the appropriate probabilities to make this less than or equal to epsilon. So, we take this matrix here. This inequality holds from the material I was covering before. Now, the very first inequality in matrix perturbation theory is that if you have two matrices, A and B, let's say, that are Hermitian, if the spectral norm of the difference is less than or equal to epsilon, then the singular values of the first and the second matrix are at most epsilon apart. So that's the number one result in matrix perturbation theory, which translates, after you manipulate this a little bit, to saying that the singular values of Vk transpose S are between root 1 minus epsilon and root 1 plus epsilon. All the singular values. So this implies full rank. Pick epsilon to be some fixed value, small value, and this implies full rank right there. So you can apply the structural result. Okay? So again, just to briefly recap before I proceed, in order for this to hold, Vk transpose S has to have full rank, and we construct the sampling probabilities, the leverage scores, that's how we chose them, so that this is satisfied. And this is just matrix multiplication, the result I showed before. Now we still have to bound the second part, so we still have to bound this term here. And one way to do it, it's not going to be the best, but it's going to be simple for me to describe in the slides, is to basically break this up in two parts using strong submultiplicativity. So you're going to break, one part is going to be this term here, and you're going to keep a Frobenius norm here. You're going to keep a spectral norm here. That's a property of when you are multiplying matrices. So that's strong submultiplicativity, basically. So you are getting an inequality of this form here. Now, the largest singular value of Vk transpose S plus the pseudo-inverse of Vk transpose S is basically 1 over the minimal singular value of Vk transpose S. That part here you already have bounds for, because you have bounds for all the singular values of Vk transpose S. And you only need to worry about this second part here, which actually is pretty simple. This is what we get. We have bounds from this. Go back a couple of slides and you're going to see bounds for all the singular values of Vk transpose S. So of course we can bound their inverse as well. The second part, in expectation, it's easy to prove, takes just a few lines, that in expectation the Frobenius norm square of this term here is basically just A minus AKF square. Using the sampling matrix there, basically, in expectation doesn't change the Frobenius norm. That's all you're going to need. Well, you're going to get a 2 plus epsilon constant factor approximation using this particular argument. To go to 1 plus epsilon, you need to do a little bit more careful analysis. And let me just highlight what the analysis that we had to do was. Instead of breaking this term up in two parts, you are going to observe that Vk transpose S, the pseudo-inverse, behaves very similarly to its transpose. Just because all its singular values are close to 1, the pseudo-inverse of this matrix and the transpose of this matrix are pretty close. Then once you have the transpose here, you have A minus AK, S transpose Vk. That's matrix multiplication. You can apply results that I had before and get the similar bound, but it's a little bit longer of an analysis, so I'm going to omit that. We use the sampling matrix. so far, and I sampled with probabilities proportional to the leverage scores. How about using a dense matrix? For example, use the random sign matrix. Same story. All I need is to make sure that the rank of VK transpose S is full. Well, the matrix multiplication result that I applied here, that I showed here for the sampling matrix, also works if this is the random sign matrix. The same analysis basically goes through. Same analysis goes through. The expectation again of A minus AK times S, the Frobenius square of that is going to be the expectation of A minus AK. Negatives, you don't have actual columns from the matrix anymore. You have linear combinations of the columns. Positives, if you can show that this matrix C, which now doesn't have actual columns, has sort of linear combinations of the columns, the span of this matrix contains very good approximations to the top k left singular vectors of the original matrix, which you can actually compute efficiently. So the span of that C, which you computed here using this dense random projection matrix, can be used now to approximate left singular vectors of your original matrix. And even this naive procedure, just using the random sign matrix there, is faster than full SVD. So this is one way to approximate the left singular vectors. Compute this AS, and then this machinery can be used to prove that the left singular vectors basically of C are good approximations to the left singular vectors of the original matrix. And you can do much better. Because instead of using this random sign matrix, you can use the fast Hunterman transform, or you can use the sparse random projection that Ken Clarkson and David Woodruff have. And then the running time goes from something like, here it was order mn c plus nc squared, it goes down to mn polylogarithmic factors on n. Implementations of this, quite a few right now. Mark Tigert has one, Joel has his own evaluations, we have our own evaluations, and they all work well. So that's a good way to approximate left singular vectors from a matrix, and a very simple one as well. Okay. Questions before I get to some more recent stuff. So this is basically the past. This is things that have been done over the past 10, 12 years.
I have a question about
Yes.
So going back to the main inequality that you just gave. So the second term, presumably the choice of S, say an optimal choice of S, depends on the norm you put.
So for unitarily invariant norms, doesn't matter. For other norms, that inequality doesn't hold. This inequality holds for unitarily invariant norms. Non-unitarily invariant norms, very different story.
Oh, but I mean, so now if you say to make the second term, the error from the second term as small as possible, you chose the particular sampling probability.
I don't know if it makes it as small as possible. I don't know if it's the optimal choice or anything like that. I'm just, if that's what I see. So all I showed is that these matrices satisfy a certain bound. Are they the best? I don't think you can break the 1 plus epsilon bound, but again, up to constants and stuff like that, perhaps there are better choices. So I don't have that. So I'm showing for specific norms, for specific choices of the matrices what happens. Okay? Okay. So some improvements, and again, let's go to the past year, year and a half, basically, what you can do. I'm going to focus on the following. Do we need, the material I have described so far, the best result I had was something like this. You pick k over epsilon square, log k over epsilon square columns, you get 1 plus epsilon approximations of the best rank k approximation. Do you need that many? Can you do better? There was a paper by Amit Deshpande and Louis Rademacher in 2010 who said that if you want exactly k columns, so I don't give you any room to play if you want, with exactly k columns, your error is going to be of the following form: root k times a minus akf. What about in between these k columns and the k over epsilon square, log k over epsilon square columns? How much room is there to play? What are you going to get? And in
How do
yeah.
you read this result?
Which one?
This one. Well, can you say a few words more? What's the
So,
assumption?
this is for any matrix, there are no assumptions, but what you are restricting yourself is you are going to pick exactly k columns from the matrix.
Yeah, this is deterministic.
This is the...
This is polynomial.
No, so this is I don't think it's algorithmic even. I don't remember if it's algorithmic, to be honest. Think of it for a minute as existential. I don't remember if it's algorithmic actually. Do you remember?
It's existential, but I think they have an algorithm too, but it's a little weaker.
I think it's, yeah. So I think the root k, they have root k plus 1, I think, for the algorithm or something like that. But this is existential. Let's think of it as existential. That's what you're going to get. There exists a subset of k counts that satisfies this. And I think they can find something that is just a little more. This you cannot improve, yeah. There is a lower bound as well. In between the two, so we had a paper a couple of years ago with my former student Christos and Malik Magno and Ismail at RPI, and what we showed there is that with 3k over epsilon columns, you can actually get relative error 1 plus epsilon approximation. So the log factor disappears, the constant is pretty small here, but also simplicity disappears. This is not like I'm going to give you now a sampling probability and you're going to sample with respect to that and get a nice result. As a matter of fact, any sampling-based procedure, because of coupon collector problems, will need the log factor there. So this is going to be different. You're going to have different procedures to do it, and as a matter of fact, our lamppost was a beautiful result, which I will describe by Nikhil Srivastava, who is here, Dan Spillman, and Josh Batson. Running times are pretty good. This is mostly theoretical. I've seen a couple of evaluations of this result actually in NIPS, I believe, this year. So there might be some nice practical uses for this kind of bound as well. The argument goes back to the same structural result. So this is a structural result I showed before. What you need now is simply a stronger control for these two terms here. So instead of having the control over the terms that I had before, I'm going to need something stronger. What am I going to need? Well, it suffices to argue that the smallest singular value of Vk transpose S is at least 1 minus root k over C. And it suffices to argue, but at the same time you need A minus AKS to be less than or equal to some constant. This is going to be actually 1 times the Frobenius norm of A minus AK. So if you can get a sampling matrix S that satisfies both these, you're good to go. Because if you set C to be k over epsilon, Vk transpose S is full rank, the result holds. Plug everything in, you get 2 plus epsilon. I'm not going to show the 1 plus epsilon, takes quite a bit more effort. As long as you can satisfy those two, you're good to go. Get a sampling matrix that satisfies these two, fine. Except you are not going to be able to do that with sampling per se, because going down to k over epsilon just doesn't work for sampling. We were able to do that. We had to generalize this result that I mentioned from Batson, Spillman, and Srivastava, but instead of actually describing the details of our own result, and then we had the second phase to actually go from 2 plus epsilon to 1 plus epsilon, I want to describe the result by Nikhil and Dan and Josh. It's a matrix multiplication result, but a very strong one actually. Let's describe it for one particular matrix, which is the one that we're going to use here, V sub k. This is a matrix that is n by k orthogonal columns, so that Vk transpose Vk is identity. Okay, so n by k matrix, k strictly less than n, but it can be literally n minus 1, the result still works. C is the sampling parameter, it's not sampling anymore, it's a selection procedure. C has to be strictly greater than k, but it can be k plus 1. Doesn't have to be k log k or anything like that. What they showed is that there exists a deterministic algorithm, no failure probability or anything like that anymore, which is expensive. The running time is Cnk cubed, so that's expensive. It creates a sampling and rescaling matrix where, again, there is no real sampling. I'm just calling that to be consistent with my own previous notation. It's basically a selection matrix. It selects a subset of columns, so that this matrix multiplication, remember this is identity, this error-bounded matrix multiplication, the spectral norm holds. The spectral norm of Vk transpose Vk minus the approximation is less than or equal to k over C. And you can set C to be k plus 1. This is much, much stronger than the kind of things we had before, at the expense of expensive time to actually figure out what is this subset of columns that you are going to select. So you spend more time to find it. Very nice. Matrix multiplication result, expensive to compute, but very accurate and deterministic. works for small values of the sampling parameter C. Again, you can set k plus 1. We always needed k log k, and there was a lower bound there also from coupon collector. Rescaling of S is important, so you're going to have some rescaling here, so when you select a column, you also rescale it, and it's non-trivial. It's nothing like 1 over the probability of sampling a particular column. The algorithm, if you want just a couple more details, it's not something I can describe easily. It's an iterative algorithm which uses barrier functions to guarantee that whichever column you include and the rescaling you do, you don't get outside, the singular values of the sampled matrix are not outside a certain regime. And the more difficult part of the proof is to argue that you can always select columns such that these barrier functions basically end up satisfying this upper bound here. So this is yet another matrix multiplication result. So far I've shown something on sampling columns from a matrix, using random projection type matrices to get approximation to matrix multiplication. This is yet another one which picks columns, rescales them appropriately, takes more time to do it, but gets very accurate results. Very good control. This is tight. There is a lower bound at k over epsilon in terms of how many columns we are going to have to pick to get relative error approximations to A minus Cx. After our work, Venkat and Ali Sinop improved actually the constant even. So we had 3k over epsilon. They can get k over epsilon plus lower order terms with a different approach, which I have not covered in this tutorial, the volume sampling methods. And there are other applications actually in QIP that I'm not going to mention here. Let me summarize a little bit the work on selecting rows and columns from a matrix. So this started with Alan Fries, Ravi Kannan, Santosh Vempala in Fox in 1998. They got basically additive error bounds for low rank approximation by sampling columns from a matrix with probabilities proportional to the Euclidean norms of those columns. And another paper that I was also involved in next year. We moved on to relative error approximations a few years later using either those leverage scores that I mentioned or a volume sampling approach, which I have not discussed, by Santosh Vempala and his group at MIT back then. We got efficient algorithms with relative error guarantees in theory when those tools were combined with random projections. Thomas Arles pioneered that, and we had other papers that expanded on this idea. Efficient algorithms with relative error guarantees and numerical implementations. I want to highlight two things here. The first one is BlenderPick, the implementation by Sivan Toledo and Chaim Avron. Michael will talk a little bit more about this. It basically beats LAPACK on its own turf by a factor of 4, and that for numerical analysts is a big deal. Actually, with Michael and Zhang Meng and Ken Clarkson and David Woodruff, we have implementations on the Elastic Cloud that can handle terabytes of data. And finally, at this point, we have optimal relative error guarantees, upper and lower bounds. So we understand a lot of things about row column sampling, at least with respect to the standard unitarily invariant norms, the Frobenius norm and the spectral norm. I have a few more minutes, so I want to talk a little bit about the two areas that we have not covered at all in this tutorial, and Michael is not going to cover them either. The first one is element-wise sampling. So far we've been talking a lot about picking rows and columns from a matrix. What if you pick elements? The procedure that Dimitris Archiopoulos and Frank Macseri pioneered in 2001 was the following. Pick elements from a matrix with probability proportional to their magnitude squared. Very simple idea. So larger elements are kept with higher probability. This is a sparsification procedure. So you take your original matrix and you sparsify it. Turns out that the sparsified matrix is close to the original matrix with respect to the spectral norm. And that gives all kinds of nice properties later on. You can approximate against singular vectors, singular values, and so on and so forth. Very nice improvement by people actually at Stanford and Berkeley. Emmanuel Candes, Ben Recht, Terry Tao, Martin Wainwright, and others worked on getting exact reconstruction from uniform samples from the matrix. Under a couple of assumptions, the matrix must be rank exactly k, and also the leverage scores, basically, the coherence of the matrix has to be bounded both with respect to the left and the right singular vectors. That is much more complicated, necessitates trace minimization. That's a convex relaxation for rank minimization, which again shows the most computationally expensive tool that I had to use for the CX factorizations and all the raw column sampling procedures is basically least squares. However, rows and columns preserve a lot of structure. So you pick a whole row, you pick a whole column. When you go to elements, there is much less structure. And that's why it's more difficult, that's why you need more expensive toolboxes there. The general problem, whether you can generalize this to matrices that are not rank exactly K, get rid of assumptions about uniform leverage, and there has been some recent progress on this, is still open. Also, how to speed up the trace minimization part. So there are a lot of nice questions in the element-wise sampling that are still open, and one can think about them before we basically make the results that exist for element-wise sampling comparable to what exists for row and column sampling. And let me say that anything in between, so those are extremes, right? You pick rows and columns, you pick elements. Can you think about blocks? We don't know anything. So anything in between those two extremes, we just don't know. The second area that I did not cover is solving problems of this form. Now, Michael is going to cover some here, and I'm going to discuss this, some material here, I'm going to discuss this. This is the holy grail of numerical linear algebra. You want to solve to figure out a solution to AX minus B that minimizes the L2 norm of the error when A is over-constrained or under-constrained. So if A is an m by n matrix, m much larger than n or m much smaller than n, we know a lot of things about that. Michael will talk about this right after the break. There is still work to be done when A is sparse. Recent progress includes the work by Clarkson and Woodruff and Michael and Zangri in stock this year, but there are still open problems on how fast you can solve systems regression problems when the input matrix is sparse and over-constrained or under-constrained. A very interesting case is, of course, when A is a square matrix. So you now have systems of linear equations. And that work here pioneered by Dan Spielman and Seung-Hwa Teng, when the input matrix A is Laplacian, the current best result is that you can actually get very good approximations, relative error approximations to the actual solution in time that is proportional to the number of non-zero entries of A times a single log factor. And that is due to Yanis Koutis, Gary Miller, and Richard Peng from a couple of Fox papers a couple of years ago. The main tool there is sparsification. But because the input is Laplacian, you have a graph, and you can sparsify that graph using a bunch of tools that have been designed specifically for graphs. And in particular, they use the idea of effective resistances and so on. Can you move beyond Laplacians? Well, the problem is that in all existing work, graphs are used in a very critical way. So going beyond Laplacians seems pretty hard. As a matter of fact, what I have here is probably infeasible, totally out of reach right now. Going to, say, positive semi-definite matrices. From Laplacians, this seems to be very hard. But perhaps matrices from certain classes of elliptic PDEs, things like that might actually be possible. And there is a little bit of work by Sivan Toledo and Chaim Avron on how you can move a little bit beyond Laplacians at this point.
What about stuff is randomized catch march?
I'm sorry?
Randomized catch march. How does it fit in?
The randomized? Hadamard?
Randomized catch march.
I don't.
Well, there is a paper by Vashinen which shows that if you did length square sampling, Kaczmark gives you exponential.
Oh, Kaczmark, yeah. So
we didn't know. We didn't know the pronunciation.
There have been a few papers that basically show that that method converges as well a little bit faster if you are using basically row and column square sampling there. Not just Versinin, I think Tasso Zouzias also has another paper there where he presents that. Yeah. So there are a couple of papers there, but they don't directly get into this particular framework actually.
They do. They have least squares.
They handle least squares, but again, that's not. So the case I specifically want to emphasize here is the square case, which I don't think they get to. I have to look into them again. I don't remember off the top of my head, I guess, but I don't think they handle directly this particular case. Okay, let me summarize. So in this first part of the tutorial, most of the effort has been on randomization and sampling, arguing that they can be used as a resource to solve problems that are massive or computationally expensive, and By massive, I mean matrices that don't fit in RAM and you want to approximate left and right singular vectors. Computationally expensive, I mean selecting, for example, a subset of good columns from your matrix. Carefully sampling rows or columns of the matrix gives you an advantage. You can construct a sketch of the matrix which basically behaves like the original matrix in terms of singular values and singular vectors. Or, alternatively, if you don't want to sample carefully, you can pre-process your matrix using those random projections, those dense matrices S. Then you can basically just do uniform sampling, essentially. But this pre-processing here allows you to get around the careful sampling of rows and columns. And Michael's going to follow up and show how these ideas can be applied to least squares problems, Nystrom method, and how they actually behave when you have terascale matrices. Thank you very much. That concludes the first part.
Oh, he finished 1 minute before his time. For questions, even though it's lunchtime.
Yes, please.
Where was the bottleneck for the computation? Where was the expensive part?
So they have to use 3 different toolboxes, actually. So they have to use preconditioners. That takes some time because they have to create a chain of preconditioners. That's sort of at the end. The part which is most immediately relevant to the stuff I described is how to sparsify a Laplacian. In order to sparsify a Laplacian, you use the notion of effective resistances. Those basically tell you which edges are more critical to keep in the graph. Computing the effective resistances has been hard. I'm sorry?
And they search.
And they search, in order to compute the effective resistance, actually they now have a theoretical tool that was the contribution by Miller and Peng, which basically does it by low stretch spanning trees. Whether it's practical or not, it's a different question. There are implementations that don't use the low stretch spanning trees that seem to work well in practice, actually. There was an article in CACM that described some of these implementations a few months ago. Okay?
Anything else? All right. Lunchtime officially. See you back here in a minute and a half.